Okay, anybody want to see any of the homework problems? I guess kind of the thing to keep in mind in the homework problems, I mean, there's the ones that I've given so far. You're just using F net equals mass times acceleration. I spent most of last class talking about the rules for free body diagrams, but if all you're calculating is the net force in a problem, you don't have to draw a free body diagram because it doesn't help you at all. You know, the net force is just everything added together. A free body diagram is individual forces. So you finish the free body diagram, you're right back where you started, just calculating mass times acceleration. But the one thing that I wanted to say about those problems is you always have to think to yourself, what is the inertial coordinate system, or what is an inertial coordinate system, you know? At least one of those problems you had to do as like a relative motion problem. You could calculate the acceleration. I think it's like, think about the one with the Ferris wheel on the train. Well, F net equals ma. You could use the coordinate system that's fixed to the train and calculate the acceleration, the observed acceleration in that coordinate system, and calculate F net based on that. But it would be wrong because the train is also accelerating. So you have to use relative motion on that problem. Are you with me on that? Anybody? Anybody looked at the assignment yet? Here. So it's one like this. You have, I think it's number 3. You have a Ferris wheel. It actually doesn't matter which way the Ferris wheel's going. And then you have a train car. That's accelerating perpendicularly. I don't remember what the magnitudes of these are. Anybody remember that?
The increment velocity was 1.2 per second.
Okay.
The acceleration was 2.5.
Okay, so 2.5. It's just a matter of your perspective, whether it's going into the page or out of the page. Let's say it's going into the page, 2.5 meters per second squared. Okay, well, what if you put a coordinate system here, you know? Let's call this coordinate system C for the center of that circular motion, okay? Then to calculate the acceleration of this point down here as it moves around, you would use the watermelon equation, okay? But if you use that with Newton's second law, you get an incorrect net force because you also have to take into account the acceleration of that coordinate system C. So what you really want to use is, you know, a coordinate system G that's fixed to the ground, and then the acceleration of, so let's say this is the passenger P. The acceleration of the passenger relative to the ground is equal to the acceleration of the passenger relative to the center of the circle plus the acceleration of the center of the circle relative to the ground. This one is the 2.5 into the page. This one is the watermelon. And then when you use Newton's second law, it says F net is equal to the mass times the acceleration of the passenger relative to the ground, because the ground is an inertial coordinate system. Okay? Any questions about that? You're like, we didn't even ask you to look at that question in the first place. But you always have to ask yourself with Newton's second law, am I measuring my accelerations in an inertial coordinate system? Or is that coordinate system accelerating or rotating? Okay? If it's either one of those, you're going to need to deal with that fact. Okay. So last time we talked about, we've started talking about the three forces with known directions, and the one force that you'll see a lot with an unknown direction. So those are pushing contacts, pulling contacts that you can always think of as replacing the contact with a cable, and friction. And we talked about pushing. I'll do an example that has pushing and pulling in it after I finish talking about pulling forces. So pulling contact that we can also think of as cable forces. Well, these forces are always parallel to the cable, or what would be the cable if you imagined one there. And away from the chosen body. Remember, pushing contacts are toward the chosen body. So for example, if you have, a body A that's connected to the ceiling by a cable, and there's an external force of 50 newtons like that, the free body diagram for this block A would have a weight force. It would have that applied force. We don't have to know what's causing that force. That's just given to us. And then for the pulling force, since this is connected by a cable, it's a pulling force. If you try to push with a cable, it just collapses. So all they can do is pull. It's going to be parallel to that cable and then away from the chosen body. And I'll usually give it the variable T for tension. One thing that you should notice, so for any cable, that touches nothing but pulleys between bodies. Okay, so it can touch pulleys or not touch pulleys, but it can't touch emus. That's what that was in my picture, an emu. Then the cable tension, T, is the same the whole way along the cable. as long as these conditions are met. So if the cable is treated as massless, and the pulleys are treated as frictionless and massless, that seems like a lot of assumptions, but those are usually pretty good assumptions if you're dealing with big forces compared to the weights of the cables and the weights of the pulleys. We will talk later about how you would incorporate the mass of a pulley into problems like that. Dealing with the friction of a pulley is easy. You just figure out what the force is and add it in there. But dealing with the mass can be, takes a little more thought. Okay, so let's do an example problem. So let's say we have a cart here. And it's connected to a cable that's supposed to be horizontal. And let's say this is 10 kilograms. And then it's connected to a hanging mass. Of 5 kilograms. And we want to figure out what's the acceleration of the 10 kilogram cart. Well, we're going to have to draw free body diagrams and use Newton's second law for both of these two bodies. So free body diagram for the 10 kilogram cart. There's a weight force down of 10 times 9.81. There's a pushing force from the ground. So the surface of contact is horizontal. That means the pushing force is vertical and toward the body. So I'll write that as N. And then we have a pulling force from that cable. So it's parallel to the cable, away from the body. Do we know what the magnitude of that force is? This question is a trap. No, we don't. If this was statics, we would know that that cable tension is just the weight of this thing. So in a way, this is one place where statics can give you sort of bad habits, okay? But because of the acceleration, we don't know that cable tension is not just going to be the weight of that hanging thing. So we just have to put this in here for now as T. And let's go to Newton's second law for this thing. We don't have any inclines or any reason to use any funky coordinate systems in this, like you would have in physics 1 for like friction problems on inclines. So let's just, for both of these two bodies, use a coordinate system like that. So Newton's second law says T0. Can everybody see that that force vector is T0? Like one way you can think of these as the arrow is a unit vector. It's showing the direction of a unit vector, and the variable is the magnitude of the vector. So you can think of this as a magnitude T times the unit vector in the x direction. Okay. Same thing with n. That's n times 0, 1 plus 0, negative 98.1. This thing can only move along the x direction, so I'm going to just put this in as a0. Okay. So we get an x equation here that says t is equal to, I left off the mass because I'm stupid, 10. So t is equal to 10a. The second equation says n is equal to 98.1. Since we're trying to calculate the acceleration and that only depends on the x equation, I'm just going to write this in here for now and set it aside. We can't solve it because we have two variables. Okay. Any questions about that first one? Yeah. That is, the thing has a mass of 10 times 9.81 for gravity. And now free body diagram of the hanging mass. We know it has a weight downwards. So this is 5 times 9.81, so 49.05. And now, I mean, if you see it something like this and it doesn't say anything about the cables and pulleys, it means that you're going to treat those as massless and frictionless and everything. So this is one cable that just goes through pulleys, which means that the magnitude of that force, that cable tension, is the same on both bodies. It's just the direction that's changed. Okay? And so this is going to be an upward force T. Okay, well, Newton's second law. So this is going to say 0t plus 0, negative 49.05 is equal to the mass times the acceleration. But, okay, so I'm going to write this first as the acceleration is just going to be in the y direction, up or down. We don't have to think about which it is. I'll just write this as, like a5 for now. But then we have to think about the relationship between the acceleration of the 10 and the acceleration of the 5. Okay. Can anyone tell me so if you assume that the 10 kilogram cart, assume that this A is positive, okay? Then that 10 kilogram cart is accelerating in the positive x direction. Which way would the 5 kilogram cart? It would actually, it would actually accelerate down. Think of it as, this always works, okay? Think of what happens, so whatever you choose as your first body, so we chose the 10 kilogram cart as the first body, and we said, okay, the acceleration is a0. Now say that it moves an inch, a positive 1 inch in the direction of that A, okay? So imagine this goes 1 inch in the positive x direction, okay? Where does this one go? 1 inch down, okay? And so what that says is the magnitudes of these are the same. But the direction of this, when this is positive A, this is like a negative A5 in Y. Okay, so so now that we've thought about those directions, I'm gonna rewrite this as 0t plus 0, negative 49.05 is equal to 5, 0, negative A. So this negative is the 1 inch thing. It doesn't have to be an inch, it could be a meter or a mile or whatever. It's just the relationships between those directions. Okay? And so now we get this equation that says t plus 5a is equal to 49.05. And now you have the two starred equations, and you can solve them as a system. Okay, so you have from the first one, t is equal to 10a. So then go into the second one, substitute the 10a in for the t. So 10a plus 5a is equal to 49.05. So 15a is 49.05. And I don't know if this is true, but I'll bet this comes out to be 3.27. Because I seem to see that number a lot. Yes! So rad. Any questions about that? Okay. How about this? So let's say that you have, this is a setup. This problem, I'm starting out like this. So you let your guard down, and then I'm gonna throw something new at you. Okay, so what's the acceleration of the 5 kilogram cart? It's not a cart, 5 kilogram mass. This one, actually, I kind of glossed over. Like, really, we want the acceleration vector from this last example. You can always get that by substituting it in. Like, when you use Newton's second law, you've always already determined what the acceleration vector is. You just have to solve for that variable. And so plug it in and you get an acceleration vector for the tan of 3.270. Okay, what's the acceleration of the 5 kilogram mass? So free body diagram of the 5. There's the outline. 5 times 9.81 is 49.05. The pulling force from the cable is this way. I'll call it T. So Newton's second law says 0t plus 0, negative 49.05 is equal to the mass times the acceleration. This is going to accelerate along the y-axis. I'm just going to put it in as 0A. Obviously, you can see, I mean, everybody knows that this is going to accelerate with the 5 kilograms down and the 3 kilograms up. But you don't even have to think about that, so don't, you know. Whatever you choose as your first body, just all you have to do is figure out what axis it's accelerating along. The signs will work out for you on their own, okay? There's no harm in saying that this is going to be negative A. It still works out fine, but there's no reason to think about that. Okay, so we get this one equation that says T minus 5A is equal to 49.05. Can't solve it because there's 2 variables, so I'll just set that aside. And then we'll go to the 3 kilogram. So free body diagram of the 3. There's a downward force of 3 times 9.81. So that's 29.43 newtons. There's a pulling force from the cable. It's parallel to the cable, away from the body. And it's the same cable as the other one, so it has to have a magnitude of force T, because that's what the other one had. So Newton's second law says 0T plus 0 negative 29.43 is equal to 3 times. Now let's think about the acceleration of this one. It's going to be in the y direction. These things are both just moving up and down. And if the 5 kilograms, so if it moves an inch in its positive direction, so if it moves an inch up, where is the 3 kilogram going to go?
Down.
An inch down, right? So we're going to call the acceleration here 0 negative A. Any questions about that? Are you with me on that? So 0 negative A. And so the equation we get from this is T plus 3A is equal to 29.43. Okay, so solve this system of equations, the 2 starred equations. Let's say, so I'm going to write the first starred equation as negative T plus 5A, I'm just taking the negative of it, is equal to negative 49.05. And the second equation says T plus 3A is equal to 29.43. And then if you add those together, you get 0 T's, so you get 8A is equal to negative 19.62. And so A is equal to negative 2.45 meters per second squared. So the acceleration vector of the 5 kilogram mass is 0. You know, we're just plugging this value now into this vector expression here. This thing here is the acceleration vector of the 5. And so it's equal to 0, negative 2.45. So without specifying on our own that the 5 kilogram is going to accelerate down, we calculated that it would accelerate down.
Mhm.
Any questions about that? Yep.
We never need to find the tension.
You never need to, but it would be easy to now, you know, just plug it back in and find it. But a lot of times I ask for both of them just as a hint to solve it as a system. But I believe what happens is the tension in that cable is somewhere in between those two.
I was wondering, does that acceleration that we found in the other problem, does that have to do with like the ratios of the mass?
Yes, it is. Yes, it does.
Because they're double. And
Yeah.
it's like a 3 to 5. So if you,
Yeah.
if you keep the proportions, the acceleration will be the same.
Yeah, that's right. That is right. If you keep the proportions, is that right?
It's always 3 to 5, you know, like if it was 6
Yeah.
to 10, let's say. Do you get
I
that?
think you're right. It seems like that makes sense.
I don't understand why our tension is between the two. It doesn't usually
Yeah.
have that.
The two weights.
Yeah.
Well,
How would the tension be like less than all of the force pulling down on it?
yeah. Well, first of all, if those were the same mass and it wasn't accelerating anywhere, that tension would,
Oh, it'd just be equal to 1.
yeah.
Okay, I see.
Yeah. Okay, but this is just the setup. Okay, so now imagine this. Okay, so now this same thing is going on attached to the ceiling of an elevator.
You're now.
This is how elevators used to look in my day. They had an elevator man pressing the buttons. Not really. And let's say that this is accelerating up at 3 meters per second squared.
Instead of doing an elevator, could we have it be in a box and there's another box?
Yes, we could, but I'm not doing that. Yes, we could do that. With another elevator over a pulley.
Oh, God.
What's the acceleration vector of that 5 kilogram mass now? Okay, why am I even asking this? Like, what does this have to do with anything? Well, here's the thing. Notice that in order to calculate the accelerations, we had to recognize that there was a relationship between those two accelerations. If this one was accelerating down, this one was accelerating up with the same magnitude, okay? For somebody inside the elevator, that relationship is still gonna hold here, okay? So in order to define the relationships between these accelerations, we still have to think of, we have to think of it in a coordinate system that's moving with the elevator. But in order to use Newton's second law, we have to use an inertial coordinate system, and this isn't it anymore because it's accelerating, okay? So to use Newton's second law, we have to have the acceleration of each one of these things relative to the ground. Okay, so we're gonna do the same stuff, but relative motion is gonna come into it. Okay. So this is more complicated now. Because the elevator is not an inertial coordinate system. Okay, so let's start with the free body diagrams. So the 5 kilogram thing, whether it's accelerating or not, what it's accelerating doesn't affect what gravity does to it. That's just 49.05 down. And the cable force still does the same thing. It parallel to the cable away from the body. But now we have to take into account the fact that the acceleration of the 5 kilogram relative to the ground is equal to the acceleration of the 5 kilogram relative to the elevator plus the acceleration of the elevator relative to the ground. Okay, this one is up at 3 meters per second squared. So the acceleration of the 5 relative to the ground is equal to, if we're in the elevator, you can think about it like if the reference frame is the elevator, you can think about it the same way that we thought about this one. So I'm just going to write this as 0A. And then I'm going to add it to 0.3 because that's the elevator relative to the ground. And so we get this thing 0 for x, a plus 3 for y. And now go to Newton's second law. We have 0t plus 0, negative 49.05 is equal to 5 times 0, a plus 3. And the equation that we can use from this says t minus 5a is equal to 49.05 plus 15, so 64.05. Any questions about that? But the key thing, I mean, you don't have to remember every step, but remember that the key thing here is we had to use the relative motion equations in order to represent this in a coordinate system, in an inertial coordinate system where we could use Newton's second law. And now we'll go to the 3. We have 29.43 t. Okay, well, what I want you to notice is the acceleration, just like in the first part of this problem before the elevator was accelerating, the acceleration vector of the 3 kilogram relative to the elevator, so for an observer inside the elevator, works the same way with that 1 inch thing, okay? So to someone inside the elevator, if the 5 accelerates up, if it moves up an inch, the 3 moves down an inch to somebody in the elevator, okay? So this is gonna be 0, negative A. That comes from the move 1 inch thing. Okay? The acceleration of the 3 relative to the ground is equal to the acceleration of the 3 relative to the elevator, plus the acceleration of the elevator relative to the ground. And so we can write this as 0, negative A plus 3. Because this is still just up at 3. Okay, are you with me? And so now we can, the acceleration relative to the ground is what we can use in Newton's second law. So now we can go to Newton's second law. And we have 0t plus 0, negative 29.43 is equal to 3 times the vector 0, negative A plus 3. And we get an equation that says t plus 3a is equal to 38.43, right? Okay, well now we have this system of 2 equations for 2 variables. So we can go, let's say, t minus 5a is equal to 64.05. And I'll subtract this second one, so minus t minus 3a is equal to minus 38.43. And you get that negative 8a is equal to 25.62. So A is equal to negative 3.20 meters per second squared. Okay, so now how do you want to report this acceleration vector? So the acceleration of the 5 relative to the elevator, that's the one that's just going to be 0, negative 3.20. Yep. That is 64.05 minus 38.43. I think. I think that's what it is.
I did already. Yeah.
You what?
I did it like with reduced rows.
Okay, you got the same thing. You can solve this any way you want. let me just write down the last one and then we'll talk about interpretation for a second. So to an observer on the ground, this thing is actually accelerating at 0, -0.2. I think the most interesting part of this answer is the acceleration to an observer on the elevator. Okay. So notice that when, like one way you could think of this is this thing was always on an elevator. Just in the first example we did, it wasn't accelerating, right? It was moving with a constant velocity or at rest. And to an observer on the elevator, then that 5 would be accelerating down at 2.45 meters per second squared. In the second example where it's accelerating up, that same observer on the elevator sees the 5 accelerating down at 3.2 meters per second squared. So it's a fundamentally different looking motion. In almost any case, you do not want to hear me try to interpret Einstein and relativity, but this is how relativity works with accelerating coordinate systems. It says, okay, you can use any coordinate system because you can't differentiate between an acceleration and a gravitational field. So an accelerating coordinate system has the same effect as changing the gravitational field. And that's what we see here. That result is the same as it would be if gravity was turned up. It's kind of cool. And if instead that elevator was accelerating down at 3 meters per second squared, it would be like, to the person in the elevator, it would just feel like gravity was turned down. But really, like what this is about is just seeing how to navigate the relative motion equations to come up with an acceleration that's in the ground frame, because that's what you need to use for Newton's second law. Any questions? I think on the on the homework at some point, there's a problem that's like this, except that instead of the pulley system being this, the pulley system is, so here's the elevator. But the pulley system is this, where like this is 5 kilograms and this is 3 kilograms.
That's just beam.
I'm pretty sure I'm not planning to sign that today. I think that's a little farther down, but how would you go about doing that? Well, think about the 1 inch thing. So let's say that you make this your first body, and you say, okay, in the elevator coordinate system, this is accelerating 0a, okay? Now think what would happen if you move this in its positive direction 1 inch. Where would this go?
Half an inch.
Half an inch, perfect, yeah. So that means that if this acceleration is going to be 0a, this acceleration is going to be 0, -0.5a. Okay. Okay, that's all.